Welcome to Study Loop.
Hello. So this is a diagram of what is going on. Okay, so we have the sphere rolling down. So the component of the weight down is going to be mg sine theta because the actual weight is mg. Okay, and of course the normal force N would be equal to mg cos theta. Okay, so we're going to be using this is just Newton's second law, F equals ma. Now this F is going to be mg, so mg is down, and then friction is in the opposite direction. So it's going to be, because it's going down, mg sine theta is bigger than the friction. So you have mg sine theta minus F equals ma. Remember this, F is friction. Now if you look at the diagram, look at the direction of the friction, it's more or less causing a torque, a rotational motion. Okay, because if there were no friction, then the sphere will not rotate, it will just flip, or to just slide down. Okay, to just slide down, it will not rotate. But because of the friction, it's rotating. So the friction is going to produce a torque. Okay, and torque is force times distance, or it's also equal to the inertia, okay, times the angular acceleration. So from this right here, if you isolate F, F will be equal to I alpha over R. And of course, alpha is equal to the linear acceleration over R. Okay, so if you do that substitution, you're going to get this. I is, like I said, the moment of inertia. Okay, so now we're going to do substitution here. So now we have mg sine theta minus F. Remember now, F is this, okay, equals ma. So if you rearrange it, you're going to get something like this, okay, because if you open the bracket, you see you have ma plus ia over r squared. So it's the same thing. Alright, so if you isolate a, because we're looking for acceleration, you're going to get that the moment of inertia for the sphere is 2 over 3 mr squared. Okay, so if you put I back in here, okay, the r's are going to cancel out. Okay, so you'll be left with this. So you can see that the I, or this portion, okay, has reduced to that because the r's have cancelled out. Of course, you can factor out the m, and then the m's will cancel out. Okay, and then you'll be left with this. So you see that the acceleration does not depend on the mass. It's only the gravity and then the angle. So if you put in the angle, then the acceleration is going to be that. And from the previous slide, we found out that the friction, F is Ia over r squared, right? Remember the inertia is 2 over 3m. So you can do the substitution and your friction is going to be equal to that. Of course, once you have friction, you know that friction is mu r. So mu is going to be what? F over r. And the r, which is the normal force, if you remember from the diagram, that's going to be mg cos theta. So if you put in the values, the coefficient of friction is going to be 0.31. Okay. Now, if you change the mass, the acceleration is not going to change, because you can see the, let me use a different color right here. You can see the acceleration does not depend on the mass. So no matter the amount of mass you use, it's still going to be this. Okay. But of course, if you look at the, what else? The friction, for example. Friction is mu r, or friction is this, right? This is friction. Friction depends on the mass. So if you increase the friction, the if you increase the mass, the friction is also going to increase, right? it's the same thing for the coefficient of friction, which is given by this, right? So if you increase the mass, it's going to affect the coefficient, because if you look at this, this is an inverse relation. So if you increase the mass, the mu is going to reduce. Okay. Thank you very much.